The last topic we're going to treat in this module is rocket motion, and that's also something where differential equations definitely come in handy. So let me sketch out this rocket here. Okay, maybe that looks more like a fish, but you get the idea. So there's exhaust coming out the back, which is moving with some velocity of the exhaust with respect to the rocket, and then the rocket itself is moving forward with some velocity v. Okay, it also has a mass, but that mass is not constant. It varies with time. That's important. It ejects mass continuously backwards, so the mass continuously decreases. So what happens during the time dt, so during the time dt, mass of minus dm is expelled with velocity vx relative to the rocket. So the reason I'm saying minus dm is because dm, the change in mass in the time dt, is less than 0. Okay, because you're losing mass. And then we're going to use momentum conservation to solve this. So we're starting out at time t. We have the total momentum of the rocket at time t is the mass of the rocket times its velocity. Then at time t plus dt, and this, by the way, should make it clear, this is the mass at time t. Okay. At time v of t plus dt, things have changed a little bit. The mass now is going to be the mass at time t plus dm. This is essentially the mass at time t plus dt. You lost some mass dm. dm is less than 0, so the mass now at this time is m plus dm. And the velocity has changed too, of course. So we now add v plus dv. So this entire thing here is the rocket momentum. Now, in order to be able to apply momentum conservation, we have to add in the momentum of the exhaust. So the exhaust is going backwards. It has a total mass of minus dm, and its velocity relative to the rocket is v exhaust, vx, which means that its velocity relative to the frame in which we are looking at the rocket is going to be v minus vx. Right, minus vx because it's moving backwards, and the rocket itself is moving forwards with some velocity v in our frame. So this is the exhaust momentum. Then we just have to write this out, all these terms. We can see that this term cancels against that term. This term here is doubly differential, so that's approximately equal to 0. We can ignore it. It can be neglected. So that is therefore equal to mv plus mdv plus the mv exhaust. Now the change in momentum from time t to time t plus dt, that is p of t plus dt minus p of t. Well, essentially this minus that which means that this mv term here goes away. So this is just m to v plus the m v exhaust. And we know that's going to be equal to 0 due to momentum conservation, because there's no external forces acting on this rocket. So we then get and then we just divide by dt, and we obtain and this equation here is known as the rocket equation. You can see this is actually equal to, this is actually Newton's second law. We have the mass times the acceleration equals some force, and this is the force of the thrust. Change in mass times the velocity of the thrust, the velocity of the exhaust. Okay. However, we're going to start from this equation here, and we're going to just integrate it. But in order to do that, we will need to move everything that has to do with mass over on one side, and everything that has to do with velocity over on the other side. So we get the v equals minus the m over m times v exhaust. Now we're integrating from our initial velocity, which will be v0, and then we obtain final velocity of v. We start out at some mass m0, and then that's decreased to a smaller mass m. Okay, and we add our primes in there to differentiate the integration variables. And when we solve that, we simply get so this is the equation for the velocity. Now the actual time evolution of the mass and the velocity is not part of this. It's something you can actually calculate for yourself, that we might be doing in class. In any case, what we can see here is that this places some very severe restrictions on the velocities that the rocket can obtain. The change in velocity that's imparted by this exhaust here is proportional to the velocity of the exhaust, but it's also proportional to the logarithm of the ratio of the initial mass to the final mass. And unless that's a very large number, the final velocity is not, relative to the initial velocity, it's not going to differ very much from the exhaust velocity. So for instance, let's say that 90% of the rocket is made of fuel. That means that the maximum value that m0 over m can take is 10. The natural log of 10 is approximately equal to 2.3. So this gives us that v minus v0 is just 2.3 times the exhaust velocity. And that's if you put 90% of the rocket's fuel. 90% of the mass of the rocket is just fuel. So in order to make a good rocket, you need essentially two things. You need a large exhaust velocity. And the second thing that you need to work with are multi-stage rockets. Okay. I'm not going to explain to you why multi-stage rockets helps. Instead, I'm going to ask you why it is that multi-stage rockets is actually advantageous if you want to obtain as high of a velocity as possible. So the question for you to ponder until class is, why do multi-stage rockets help improve rocket performance? And so there is a reason, of course, why the real rockets have them, and that's the reason I want you to come up with.